it's me again. Welcome back to Algebra 2. Today's lesson is 10.1, the beginning of sequences. Now, you looked at sequences already in Algebra 1. I think one of the most important things to remember about sequences is the domain remains fixed. All right, so it isn't like other functions or other things that we've worked on where the domain can be restricted or the domain is, the set of all real numbers. Here, the set of x values or n values or whatever your domain is are just the natural numbers. In other words, or the counting numbers. So we're counting first term, second term, third term. There's no 1.5 term. It's just like counting people. Okay, you can't have a half a people. You can't have a half a person. You can only have 1 term, 2 terms, 3 terms. And if you can keep that kind of straight in your head throughout this lesson, I think it will be much easier for you. All right, so let's look at example number 1, exercise number 1. A sequence is defined by the equation a of n is equal to 2n minus 1. Now, my apologies because how I have this written in A is not really 100% right. It says find the first 3 terms. So find the first 3 terms of this sequence denoted by a sub 1, a sub 2. I think the way I have it here, I think I would prefer to write it a of 1, a of 2, a of 3. Because if I wanted it to be this way, I should have written this as a sub n is equal to 2n minus 1. So the notations are similar, but they're not exactly the same. All right, so I have to change that for next year. My apologies. So to find the first 3 terms, they're telling us that we want to know when n is equal to 1, when n is equal to 2, and when n is equal to 3. So these are simple because this is a linear, this models, it isn't a linear function, it models a linear function because we have a of 1 is equal to 2 times 1 minus 1, which is equal to 1. A of 2 is equal to 2 times 2 minus 1, which is equal to 3. And a of 3 is equal to 2 times 3 minus 1, which is equal to 5. Now it says which term has a value of 53. So now be careful because this one is asking us something different. It's saying which term. So n, it's looking for n this time. So it wants to know what is n equal to when it has a value of 53. So they're saying a sub n has to equal 53. So is there an easy way to figure this out? I think probably the easiest way to do it is actually just keep going. So I know this is the first term. So you can go up 53 times if you want to. So I mean, I know that, well, not 53 times, but up to 53. So first term, second term, third term. So what's the pattern? Fourth, fifth, sixth, and magically, we have all of them. So, I mean, you can count here at this point now, and you can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25, 26, 27. So, what the answer to this is, n is equal to the 27th term is equal to 53. At least I'm pretty sure that's true. That's how really you can do it at this point. There are going to be some shortcuts that we can take, and we'll talk about them as the lesson progresses. All right? So C says, explain why there will not be a term that has a value of 70. Well, just by doing this, and I know it took you a little bit longer, or it would have taken you a little bit longer. My advice is you don't have to write all that down. But if you can see what this sequence is doing is generating our positive odd numbers. So it's never going to produce a positive even number. So we can base on that. Of course, it says to explain why. So let's do some explaining here. How about we can see how this sequence generates a positive odd numbers. There will not be a domain member I'm just going to put of natural numbers or counting numbers that will generate an even. And if you didn't write all those numbers down on the top, if you weren't sure, you could even generate some more of those, even up to 70, and say how that's not going to be possible. All right, so make sure if it says explain, don't leave any rock unturned. Make sure you are explaining everything that you possibly can. So recursive definitions are also, so what we just talked about is called an explicit definition, which is great because if you want to know what the 100th term is, you can just put in a of 100 or f of 100, and you can come up with that final, that term that associates with the actual value of the 100th term. But in exercise 2, we talk about recursive sequences or recursive definitions. And what these do is these depend on the term that comes before it. All right? So in exercise 2, a sequence is defined by a recursive formula. Now, this is a little scary looking until you understand what it means. If we go back to, and with the recursive formula, it has to give you the first term. So f of 1 is equal to negative 2. So how we read this f of n is equal to f of n minus 1 plus 5, is we read this as the term we're looking for is equal to the previous term plus 5. Because if we're looking for f of, so let's use exercise 2a as an example. So if we do our formula, we're given that f of 1 is equal to negative 2. So now we want to do f of 2. So in this case, n is equal to 2. So f of 2, so what we do is we put a 2 here, and we put a 2 here, and we get 2 minus 1. So it's equal to f of 1 minus 2. So it's equal to the previous term, which is negative 2, minus 2. So my answer is negative 4 for f of 2. F of 3 is equal to the previous term minus 2, which is negative 6. How many do we need? We need 5 of them. Oh, I'm sorry, I'm messing up here. I don't know where my brain was. All right, so glad you didn't write that down. For some reason, I was doing this wrong. It's f of 2 plus 5. So f of 1 is equal to negative 2. F of 2 is equal to f of 1 plus 5. I'm sorry, you were probably getting so confused as to what I was doing. So it's negative 2 plus 5, so my answer is positive 3. All right, so negative 2 plus 5, positive 3. So f of 3 is equal to f of 2 plus 5. So f of 2 was right here. So this is equal to 3 plus 5, which is equal to 8. So f of 4 is equal to the previous term plus 5, which is 13. And f of 5 is equal to the previous term plus 5, which is equal to 18. All right, so there's f of 2, f of 3, f of 4, f of 5. So you can see, actually, we would be able to make an explicit out of this because our rate of change is by 5. It adds 5 each time. So you could rewrite this. And the point that I'm saying that is because when we look at B, it says determine the value of f of 20. Usually with recursive sequences, the only way that you can do that is to find the first 20 terms. Now you can keep going the way we're going. So we're adding 5. So what do we have? We have -2, we have 3, we have 8, we have 13, we have 18. And this is 1, 2, 3, 4, 5, right? So we're looking for the value of f of 20. So we can do 6, 7, 8, 9, 10, and go all the way up to 20. And believe me, that's just as effective. A little bit longer, but it's fine. But you can also see if you wanted to make an explicit formula out of this. So finding out what that equation is sometimes can be a little difficult. But in this case, because it models a linear function, it's kind of easy to see that we add 5, we add 5. So we're going to say, let's call it f of n is equal to, and let's put it in terms of n itself. So if I say n plus 5, I'm going to get 1 plus 5, which is 7. So that's not going to work. So basically, even though n can never be 0, we have to think about what that 0 term is. So that 0 term, if you minus 5 and went backwards, we'd have a -7. All right, so that's going to be my y-intercept. But remember that we actually don't have a y-intercept, we don't have a 0 term, but to create this function, we do need that 0 term. So it's going to be our plus 5 is our slope. So it's 5n, and then we have to put -7. So think about what this is now. To find the first term, it's 5 times 1 is 5, and 5 minus 7 is -2. When n is 2, we get 5 times 2 is 10, and 10 minus 7 is 3. So that's going to work for us. So to find the 20th term, it's easier now. F of 20 is 5 times 20 minus 7, which is 100 minus 7, which is 93. You don't always have to do that, but, and again, you could just keep going that 20 terms. I don't want you to think you always have to do this. It takes you a little bit longer sometimes, but you get to the same destination. All right, so exercise 3. Determine a recursive definition in terms of f of n. So this time they want a recursive definition for the sequence shown below. Be sure to include a starting value. Well, the starting value is easy. So it doesn't matter how you create it. It can be a of 1. We're going to talk about a lot of different notations here. So don't flip out when we change it up a little bit. So let's, again, we're going to use the function f. So f of 1, so the first term is equal to 5. So what we want to do now is we want to take the second term in terms of the first term. So the second term is going to be the term before it, right? So it's going to be the term before it plus 5, because if you look, every time it's simple. Oh, it's not. It's not. It's not linear. It's times 2. All right, so take this away, and let's put, and you could even do times 2. You can do times 2. You can do a 2 out front. Probably that's how I would do it. 2 times the previous term. Does that make sense now? So if this is the first term, the second term, the third term, it's 2 times the previous term. To find the second term, it's 2 times 5, which is 10. That works. Sometimes you have to go through it in your head a little bit until it starts making sense. Okay, so let's look at exercise 4. For the recursively defined sequence. So again, recursive just means that they're giving you an equation and they're giving you the first term. And they want to know what the fourth term is. So the first thing I do with this is I kind of rewrite it in terms that I understand. So again, we're talking about different notations here. So when you see something like this t of n, I know that's the term I'm looking for. So the term I'm looking for, and this crazy looking thing here, is the previous term. And what we're doing with the previous term is we're squaring it and then we're adding 2. So if I make sense of it, the rest of it is just cake. So t of 1 is equal to 2 because they give us that right here. So t sub 2, now if I use my definition, it's the previous term squared plus 2. So this is going to be 4 plus 2, which is 6. To find the third term, it's going to be the previous term squared plus 2, which is 36 plus 2, which is 38. To find the fourth term, which is the golden ticket here, is the previous term squared plus 2. And the previous term squared is 1444 plus 2 is 1446. All right, oops, there it is, number 4. Now in exercise 5, one of the most well-known sequences is known as the Fibonacci sequence. It's basically how certain things in nature show up. Like if you looked at the petals on a flower, or if you look at how certain animals reproduce, it definitely follows the sequence of the Fibonacci. So it shows up in nature a lot. When you get into chemistry, and you get into actually probably biology, not chemistry, biology, living environment, and probably a little bit more advanced sciences than that, you'll definitely come up with this sequence again. So it's defined recursively as two previous terms, as the addition of the two previous terms. So its definition, I know it looks a little crazy, is this here. And again, it's recursive, so it has to give you the two previous terms. Because again, we're trying to make sense of what this means. This f of n is the term I'm looking for. So the term I'm looking for is the previous term, right? Because if you have n, so if you have 5, this would be f of 4. The previous term plus the term before that. So the term before the previous term. So in other words, if I'm looking for f of 3, f of 3 is going to equal to the term, so let's just write it out first. F of 2 plus f of 1. Well, I know f of 2 and f of 1 is 1 plus 1, which is 2. So, I mean, you can write it out using the definition, and then you can start just using a little common sense. So f of 4 is equal to f of 3 plus f of 2. So f of 3 we just found right here. So it's 2 plus f of 2 we were given right here. 1 is equal to 3. But as you can see, now this is where the common sense starts to play a little bit. So I'm realizing that f of 5 is equal to the two previous terms, 3 plus 2. And do we need f of, yeah, we need f of 6 is equal to the two previous terms, 5 plus 3. Right, and if you're going to do f of 7, it would be 8 plus 5, which is 13. F of 8, 13 plus 8, which is 21. So it would just keep going, the two previous terms. After a while, it becomes very elementary. You just have to get past the notation, and then the rest of it becomes pretty easy. All right, try not to overthink sequences. 6 says find the algebraic formula for a of n for each of the following sequences. Recall that the domain that you will map from is the set of natural numbers or counting numbers. All right, so this is just using a little common sense here. If you look now, if it mimics a linear function, and I know it mimics a linear function if the common difference is the same. So this one, the common difference is positive 1. It goes up by 1 each time. So that means that I kind of need to know what that 0 term is to find my slope. All right, I'm not circling the a, I'm circling what should be there. All right, so in other words, if I go from 7 to 6 to 5 to 4, to find that 0 term, it would be 3. So my formula would be a sub n, or a of n, it's equal to 1 n plus, it starts at 3, plus 3. And I put the 1 in here because 1 is my slope. It's what I'm adding each time. If I was adding 2 each time, I'd have a 2 in front of the n. And I always double check it before I move on. So when n is 1, remember this is 1, this is 2, this is 3, this is 4. When n is 1, I get 1 plus 3 is 4. When n is 2, I get 2 plus 3 is 5. When n is 3, I get 3 plus 3 is 6. So perfect, I'm right there. But not all of them are linear. Like that other one I was thinking was linear. Remember I said, oh, that's not how it works. If you go here, it looks like it's linear, but it's not. Because I add 2 to get to 4, but I add 4 to get to 8, and then I add 8 to get to 16. So I'm kind of hoping when you see this, you see right away that they are powers of 2. So this one's going to be a sub n is equal to, and this one I struggled with for just a little bit because I was like, oh, it's equal to 2n. Don't write this down. It's not right. It's 2n. And then when I checked it, I said, well, this is 2 times 1, 2, 3, 4. 2 times 1 is 2. Okay. But 2 times 2 is 4. Okay. 2 times 3 is not 8. 2 times 3 is 6. So right away, I thought to myself, okay, that's not going to work. So I started thinking to myself, all right, 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. Then I finally got the answer. And C, the only thing that's changing is the numerator here. If you remember in the first term, it's really 5 over 1. So this one's simply going to be A of n is equal to n over 5. Right? So when n is 1, you get 1 over 5. Oh, I just wrote it backwards. What is wrong with me today? Equals. It's been a long day. So this is going to be 5 over n. That's why it's really important, even for seasoned mathematicians, to look at your answer and make sure that it matches what you want it to produce. All right? So, because I'm telling you, it's the only thing that separates you from me is that I know enough to check my work. All right? And you're going to get to that point too, and then you're going to be as smart as all your math teachers. All right. Now with D, because it goes negative and negative positive, I know that it's going to have a -1 with a power. And you're going to see this a little bit when we get to summation notation. So what's happening here goes -1 then to +1. So right away, I know that it's going to be -1 to a power. So it's either going to be n or n plus 1. This is the first, the second, the third, the fourth. So when I do to an even power, it's going to turn positive. So I'm okay just putting to the nth power here. Because when it's odd, it's negative. When it's even, it's positive. So that's easy enough. 10, 15, 20, 25. This one's a linear, right? Plus 5 each time. So I add 5 each time, and I know that's my slope. So a sub n is equal to 5n. Now I need to know what that 0 term is. And so here's the first, the second, the third. I need to know what the 0 term is. So I think it's pretty obvious to see that the 0 term is 5, because instead of adding 5, you subtract 5. So plus 5, and then I check it. When n is 1, 5 times 1 is 5, and 5 plus 5 is 10. When n is 2, 5 times 2 is 10, and 10 plus 5 is 15. Works beautifully. And the last one, 4, 9, 16. Right away, I see perfect squares. You know me, I love my perfect squares. So I'm going to remind you that here's my first term, my second term, my third term, my fourth term. So I'm going to have a sub n is equal to, it can't just be n squared, it's got to be 1 over n squared, right? Because I get, when n is 1, I get 1 over 1, which is 1. When n is 2, I get 1 over 2 squared, which is 4. When n is 3, I get 1 over 3 squared, which is 9. That works. All right, so again, I just make sure. It might take you a couple tries before it makes sense. I'm a little bit more seasoned at this, and as you see, I'm not perfect at it because I think I made 2 or 3 mistakes doing this one. All right? So moving on to exercise 7. And this is the last one. I know we're getting a little long-winded here. Which of the following would represent the graph of the sequence? Now, if you remember, and it says explain your choice. So if you remember, a sub n equals 2m plus 1. So you're looking at this, because I know you're looking at this saying, this is linear. This models a linear function, 2m plus 1, mx plus b. And then you look at all your answer choices and you're like, dang, they all look linear. They all kind of model a linear function. But I want you to recognize, what is the domain? What is the, so I'm going to say the domain of here starts with what number? The domain starts with 1, 2, 3, and so on. They're the counting numbers. We're counting the first term, the second term, the third term. We generally, when we count, we don't say, oh, this is 1, this is 1.5, this is 2, this is 2.5, this is 3. That doesn't even make sense to be able to count that way. And what makes even less sense is this is -1, -2. Okay, we're going to count. You start with -5. No, you're counting, you start always with 1. So if you take a look at numbers 1 and 2, what does the domain start with? Well, if you look very carefully, we have 0 being in the domain. So therefore, we know that 1 and 2, so we know that 1 and 2 has 0 in the domain. So therefore, we can exclude them. Now, it says to explain. I'm kind of just making comments here and versus explaining. Of course, if you were going to explain this, you'd make it a nice, beautiful paragraph. So we're going to get rid of 1 and 2. Now, the second thing is, if you take a look now between 3 and 4, one of them has the points connected and the other one doesn't. This over here, this is called discrete, and this is called continuous. And if you think about like water filling up a pool out of a hose, that's going to be continuous. So if you consider like the number of seconds that go by, or maybe the number of minutes that go by, you know, you can get to 1 minute, you can get to 1.2 minutes, you can get to 1.5 minutes, you can get to 1.8 minutes. So you're going to have numbers, you're going to have values between 1 and 2. But when you talk about a sequence, you're talking about discrete, because you're talking about the first term. So hold on one second, move this down a little bit. You're talking about the first term, the second term, the third term, the fourth term, the fifth term, the sixth term, the seventh term. All right, so you're not talking about the 1.5 term. All right, because there is no such thing. There's the first term, the second term, the third term. All right, so now I'm going to say here that number 4 is continuous. And that we're going to exclude or omit. All right, and here you would spend a little bit of time explaining, because you don't have a 1.5 term or a 1.2 term. You only have a first, a second, a third, a fourth, and so on. So the correct answer here is number 3. If you need a little bit more clarification about that, ask me during class tomorrow, and I'll be happy to spend a little bit more time on it, and maybe even write out what a really good explanation would look like. All right, so I think with the information you have there, you could probably take just a moment or two and write out a complete definition or a complete explanation of what they would want here. Something along the lines of number 3 is the correct answer because the points are not connected and the domain is appropriate and begins at number 1. So, I mean, that's not a terribly long explanation, but I think it gets the point across. And if you use words like discrete versus continuous, that would only be a bonus. But again, I always tell you, when you're explaining, my advice is try to explain it like you're explaining it to your grandmother. Don't use the crazy mathematical language that you know we always like to use in class. But when you're explaining, I don't want you to think that that complex, all right? Because there's a lot of different ways that we can use discrete and continuous and domain. You could use x values. So there's so many different, or n values in this case. There's so many different ways that we can explain things without making it so crazy. All right, so until next time, like I always tell you, make good choices. All right, be kind to each other. And um, I didn't know if I said it, but see you next time. Bye.